Hello, everyone. Welcome to our webinar today. This webinar is a presentation of the Energy Storage Technology Advancement Partnership, and the topic for today's webinar is the AI power problem, why battery storage is crucial to data center development. And we have an excellent panel of guest speakers with us today, but before I pass it over to them, I'd like to go over a few webinar logistics. All attendees are in listen-only mode, so your webcam and microphone are disabled. The chat function is also disabled, so if you would like to submit questions and comments, you can do so via the Q&A panel. We'll be saving about 15 to 20 minutes at the end of the webinar to address audience questions, so please submit your questions throughout the webinar as you think of them, and we'll get to them after the discussion. Automated captions are available. The speakers' bios will be made available in the chat as they're being introduced. And finally, this webinar is being recorded. We will email you a webinar recording within 48 hours, and it will also be posted to CISA's website at cisa.org/webinars. A little introduction to CISA. If you don't know, the Clean Energy States Alliance is a national nonprofit coalition of public agencies and organizations working together to advance clean energy. CISA members, which are mostly state agencies, include many of the most innovative, successful, and influential public funders of clean energy initiatives across the country. And on this slide, you can see all of our member organizations. And as I said before, this is a presentation of the Energy Storage Technology Advancement Partnership, which facilitates public and private partnerships to support joint federal and state energy storage demonstration project deployment, supporting state energy storage efforts with technical policy and program assistance, and disseminating information to stakeholders through webinars, reports, case studies, and conference presentations. And you can learn more about this program at cisa.org/STAP. And with that, I'd like to pass it over to our host for today, my colleague, Abbe Ramanan.
Thanks, Irene. Hello, everyone. My name is Abbe Ramanan, and I'm a project director at CISA's sister nonprofit, Clean Energy Group. Clean Energy Group works at the forefront of energy innovation to enable affordable, reliable, clean energy for all. Among other projects, I lead CEG's Data Center Energy Accountability Initiative, which works with regulators, policymakers, and community advocates to protect energy affordability and community health in the era of data center expansion. Some of you may notice that my colleague Todd Olinsky-Paul was originally going to join us, but he's out this week, so I will be doing a little bit of double duty as both a moderator as well as a panelist. And I am joined today by David Chernis, Director of Flexible Compute Platforms at CPower, one of the leading virtual power plant platforms in the country. For more information about David, we've shared his bio in the chat, and I encourage you to take a look. This webinar is going to be in a slightly different format than most CISA webinars, in that we will not be using slides. Instead, David and I will be spending the next half hour or so discussing the value of energy storage as data center infrastructure, followed by what we're hoping will be a robust Q&A with you all, the audience. So I encourage you to submit questions via the question box as we're speaking, and we'll do our best to get to as many as we can in about the last 20 minutes of the webinar. If there are any questions we don't get to during that time, we'll be sure to follow up with you all via email. So with that, I'll turn to you, David. David, data center load growth is pretty much on everyone's minds at the moment. Lawrence Berkeley National Lab just released an update to their 2024 data center energy usage report in the last couple of days or so. And their revised projections indicate that data center energy usage could account for 11.8% of US electricity usage by 2030, although that's kind of in the middle of the estimated range, which could go as high as 15.3%. EPRI also released updated projections that indicate that energy usage from data centers could be as high as 17% of total US electricity usage by 2030. That's about a 60% increase from their 2024 projections. So we're seeing kind of exponential growth here. These are astronomical figures. And there's obviously some concerns about having adequate grid capacity to meet this demand. So, we're hoping you might get into some possible solutions for this issue. But before we get into the solutions, I wondered if you could kind of break down the different segments of data center demand, because they're obviously not all equal. Could you go over the different segments of sort of those compute-focused large load customers that your company works with, how their demand profiles might differ, and which segments are likely driving most of these sort of future growth projections?
Happy to, yeah. And thanks for having me on today, Abby. I'm really excited to have this conversation with you. As you outlined there, you know, load on the U.S. grid has been decreasing since the 1970s, with just kind of power optimization. And while the utilities and the grid operators had been planning for some rise in load through new technologies coming online, traditional data centers being one of those, it wasn't until the rapid rise in adoption in the US of ChatGPT, the beginning of generative AI, and now we have agentic AI, really creating that hockey stick that we just outlined. The three types of I like to think of data centers in three different segments. So all the way over here on the left, the most flexible loads that we have in our stable are the is the blockchain sector. So the uh, cryptocurrency miners in Texas, PJM, New York, the Midwest, uh, they, because they're so flexible and can get offline in minutes to seconds now with full automation responding to signals directly from the grid operator or the local utilities, that we think of them really as a digital battery. We've been doing that for 4 or 5 years now, fully automated. And because they're not hosting Netflix or supporting, Wall Street transactions or anything like that, they were a very flexible digital resource, fully flexible compute type. So that's where we've been kind of cutting our teeth and understanding how we can do this in the white space on the load side. All the way on the other side of the spectrum is the traditional data center. Most of them, if they're not an enterprise uh, class, hyperscale, single use owner operator data center, most likely the most common model there is the real estate investment trust, where the data center is an infrastructure company, a real estate company. If you think about a host, a tenant, and a landlord arrangement where the energy costs are passed through to the tenant, um, they're the idea of flexing compute inside the white space is a very foreign idea to a traditional data center, and nor would that compute be able to be flexed. There's 99.999 uptime requirement for the service level agreement, quality of service. But our traditional data center customers do help support the grid on those 50 peak hours, and just to simplify this and create a very high level example here. We're just trying to solve for, let's say, the 50 peak hours. It varies by region and by weather conditions, but it's air conditioning load that is creating this shortfall. Here's where the grid operates on a normal day. Those 50 peak hours, we have to provide this 80, 90, 100 gigawatts of power just to meet air conditioning demand on the hottest 50 hours. So that's the goal here. So the traditional data center operators will switch to their backup gens, their compliant backup gens, diesel or natural gas, and go offline for those 4 hours in the afternoon on that peak day. And but then in the middle, the rising class of new data center, the AI factory or neo cloud host, this is a new design build, a new opportunity for us to design the right kind of data centers that we need to meet the moment to get us to 2030 when new generation will be coming online. And what we'll be talking about today, what I'm arguing a bit for, is back these AI factories, small, medium, and large, fully with battery storage to get us offline, to get us to help solve those 50 peak hours. Uh, if we can get those large loads off for those 50 peak hours, we have another 100 gigawatts to play with to do all the things we want to do in the US with AI infrastructure. And it is AI infrastructure that is the fastest growing load segment there. I'll just pause there if you want to drill into any of those points.
Yeah, I did just want to kind of ask a clarifying question there, David. When you alluded to the air conditioning, you're referring to sort of the cooling load for most data centers. Were you kind of saying that that's one of the biggest drivers of energy usage among just that segment or overall?
there was an interesting cover story in MIT magazine, I think like 3 months ago. The largest global load, and the reason we have this problem, and the reason we're in business as a demand response company, is it's really air conditioning load, not just for data centers, but globally, and that's growing in developing nations. Um, Certainly, like in the EU, air conditioning is not very common, but it's becoming increasingly common. So we're really trying to solve for air conditioning load. That is the biggest global load, and then a couple other things below that, and then data centers. Um, I will comment that again, back to the AI factory design opportunity we have here now, was just at Data Center World, and Align Digital made a very interesting comment talking about air conditioning. Traditional data centers are air conditioned, right? They're just football field size white room with air conditioning and evaporative chillers. AI factories, because of their thermal and their energy density, it's a direct liquid cooling type of cooling, and not air conditioning, which uses almost no water. Aligned with saying they're using like 100 gallons a year because the cooling loop is enclosed, so there is no evaporation. What is that, like 2 bathtubs worth of water? So the air conditioning footprint of AI factories, and I especially like them small to mid-size, so they're not such a whale getting touching down in the community and having such massive impact if we make these things smaller. But yeah, there's new innovation in cooling also, which uses less water. But yes, the global problem is air conditioning globally.
Got it. Thanks for that clarification. Yeah, and I'm the one who kind of got you off topic here, but I do want to get back to sort of your definition of the segment of AI factories a little bit, because I know, I think everyone's aware of sort of the hyperscale data center. That's kind of the one that's on everyone's minds because they can represent sometimes gigawatts of load. So yeah, if you could just break down a little bit that small, mid-size, large, in terms of size of the AI factory a little bit.
Yeah, and this will tie into, interconnection queues, that's the bottleneck that we have right now. So I'm a big proponent of small to mid-size distributed networks, like DERs, but distributed networks of compute. Um, and we can think about that, looking at some of the EPRI models, the great work they're doing over there with DC Flex. Uh, we have the hyperscale model. We're aware of what's happening there, where we're bringing our own generation. Um, we're bringing our own capacity. We'll get into that in a bit. But small to mid-size, you can just back that 100% with storage and fast track through the interconnection. And you're not a liability for the grid for those 50 hours that we're trying to solve for because there's so much cooling load. You could pop offline for those 50 hours, fully island behind the BESS, the storage, and that kind of solves every problem. I know we're going to get into the four attributes of that in maybe the next segment, but I was talking to an economist, a real estate economist, at a recent conference last month, and he showed everybody like some interesting figures. So if the cost of AI infrastructure is somewhere between, this is a big bracket, somewhere between $3 million and $17 million per gigawatt to build, and battery storage is $1 to $2 million to fully surround your infra with a flexible resource, for the four reasons I won't divulge now that we'll get into later. That's not a big incremental cost to support the grid, get your conditional megawatts, and connect quickly. So to me, I mean, a couple of $1 million against 10 or 12 million. I mean, it's a lot of money, yes, but the capital is there to do that. So why not just design them that way?
Right. And as you're kind of alluding to, and I think what everyone's eager to get to is, we have this huge sort of gap in grid capacity and growing demand, and this sort of cliff we're seeing at around 2030, and trying to figure out how we can solve for those capacity constraints and how we can potentially use data centers as more of a grid asset rather than a grid liability. So, in parallel to this data center growth story, we also have what could potentially be a virtual power plant growth story, or VPP, or demand response story. DOE estimates that 80 to 160 gigawatts of VPPs by 2030 could meet 10 to 20% of US peak demand, while saving about 10 billion annually in grid costs. That's a huge opportunity. This is something that we at CISA and CEG are very focused on. We actually just launched a VPP acceleration initiative. You started alluding to this a little bit. I wonder if you could just get into how energy storage can unlock demand response and virtual power plant program participation for these AI factory customers, and the specific value not only that they can bring to the grid through energy storage, but then also the value that energy storage can bring to the customer themselves.
I love this topic. Thank you. Yeah, so we're gonna talk about this at the mid scale. Certainly there's the hyperscale, and then there's the macro scale. Just to follow up on that last point about EPRI, so we don't have to think about everything at the hyperscale. We can pair a single GPU or two GPUs with residential storage. There's some companies coming to market now where we spread out the compute across a community. And I'll talk about why that helps the community in my fifth point here. But pairing storage with compute, to me, solves this problem. It gets us to 2030. And like going back to let's go back to the mid-size example, the most common case here for AI factory design. The four reasons I'm a big believer that battery storage is the problem, the answer to this solution. One, mechanical generation, whether that's on-site, if you're a hyperscaler, you're bringing your own, you're building your own generation, you're operating your own power plant to get speed to power. Mechanical generation, let's say combined cycle natural gas generation, that's a mechanical load, a mechanical generator, a turbine spinning that was designed to feed another mechanical load, heavy industry where there's a machine also spinning and it's a very flat baseline, right? It's a mechanical generation source for a mechanical load. Now, because of AI, the way that GPUs handle workloads, let's take inference compute example, because inference is rapidly becoming the more predominant load type and compute type.
And I'm going to ask you to define inference for the maybe not as AI focused folks on the call.
Sure, yeah. So when we started off in this AI revolution, this technological revolution here, most of the workloads were training workloads, training of large language models. And think of that as you're building a book. You're training a large language model to be knowledgeable about either one specific thing or everything. Now that we have the large language models built, the workload types are inference workloads. So you're actually whether you're using AI of your choice at work or at home, you're querying that large language model for an answer and an output. If you're like a biotech company doing medical research out of New England or wherever, maybe you're taking this big research project and you're querying a large language model or a very specific model to get an answer over minutes, days, hours, whatever that compute period is. So inference workloads, becoming the most common type of AI compute, are very spiky. You have all of these GPUs, graphic processing units, which are the compute building block. You can go from a 0 power use to 100% power use in milliseconds, and you might have 5 or 10 megawatt clusters moving like this. And then if there's not a workload scheduled right behind that one, it'll go back down to 0. Not only is that bad for your on-site generation, it's bad for the grid. If you stand next to a gas turbine generator trying to ingest or match those spiky loads going from 0 to 100% in milliseconds, you can hear the turbine spinning up and down. It's as if you're Imagine you're on the highway and you're just flooring your gas pedal, letting off, flooring your gas pedal, letting off for days at a time. You're here to wear your engine out, and that's what we're seeing. We're seeing torsion, like metal fatigue at the shaft, and we're starting to see like 7 months in, people are snapping shafts on their brand new combined cycle natural gas. So reason one, very long-winded. I apologize, Abby. Reason one, tame the transient peaks so you don't damage your on-site generation and so you don't damage the grid generation. Number two, the AI infrastructure, the compute is very sensitive to low voltage sags, and we're starting to see more of those. We're seeing them here in the Northeast where I am, Ohio. We're getting complaints from our food manufacturing and our advanced manufacturing customers that they're, micro voltage sags or like mini brownouts are affecting their equipment. And they're putting in flywheels and UPS systems. So reason number two is protect your AI infrastructure from low voltage ride through coming from the utility. And I would wager that some of that low voltage ride through may be getting caused by spiky loads coming online and going straight to grid. So reason two, power quality coming in. Reason one was power smoothing going out. Reason three, fast interconnection. That is the problem, right? The bottleneck. We're just trying to solve for those 50 hours, check the box for the utility, especially if you're in PJM or Texas, where SB6 is now signed into law, and check the box for the grid operator. Problem solved, fast interconnection, and there's regulation being discussed now, as you'll detail later in the other segment. Number four, you can actually get paid to play in these power markets as a generation asset would, a virtual power plant. You're still acting as a power plant. There are really lucrative demand response programs that pay for those megawatts in the hours that the grid needs them back. That's what we do. And I'll tag on to the end of that. With the community pushback becoming another bottleneck, understandably for some of these hyperscale developments, they are quite large and they do have a community impact. If you listen to what Shell Izzy at PG&E is saying, and some of our other leaders at the utility level, large loads coming online actually spread out distribution costs. And a lot of these loads aren't even online yet. The ratepayer increase is coming from other factors, but in terms of that, not in my backyard in the ratepayer increase concern, the idea of bring your own capacity is gaining traction in PJM, which incentivizes the local community. They actually get paid at a higher level than even the commercial and industrial customers that we work with would. So that gives community benefit to help support the mid-size or large data center to come into that community and actually keeps the lights on the hottest days if they bring storage. So that's kind of the fifth reason is community benefit and creating a new demand response transaction where the local businesses and residential community gets incentivized.
Great. Well, I think that was a great outline for and not long-winded at all for kind of the benefits that energy storage can have for both the customer and the grid. But this all sounds great. I think we have heard a lot of pushback from data center developers about energy storage because they cite the need for firm generation for on-site power that's gas turbines or in some more theoretical cases, small modular reactors, SMRs. You kind of alluded to this a little bit, but I wonder if you could get into just how different energy storage technologies can still provide that firm generation, especially again, in complement to other sources of on-site power. So maybe, you do have a gas generator or you are co-located with solar or wind, but you also have that energy storage. And I know your company is a little technology agnostic in terms of energy storage, but maybe in your experience, you've seen what is most common for your customers.
Yeah, well, I mean, it's such an exciting time. There are so many of our partner companies innovating in this space and just new models are emerging every day. I talked about the kind of mental fatigue and the torsional stress issue. If you are going to if you are going to bring your own generation, um, talking to developers who are doing just that, generation builders, developers, our parent company, NRG, builds generation. Having storage there, and by storage, it's a blanket term. I'm including kind of sophisticated new UPS systems that are coming from our partners at Vertiv or Generac. FlexGen is a really interesting company that does just this, protects generation from spiky AI loads. Form Energy is interesting. They have a 100-hour utility scale battery. So yeah, the idea of storage is as the container, right? That we're storing cheap energy in, or storing any on-site generation in there to release at the most constrained high cost, high demand hours. So it's just redistributing the megawatts so that when they're acutely needed by the grid, we could give them back and keep costs low for the site, protect the infrastructure, um, and yeah, I think, for us, it's in all of the above. It's all of the above. It's on-site generation, whatever that looks like, whatever technology that is, natural gas or otherwise. Small modular nuclear is a really interesting idea. I think that we're years away, in my opinion, from deployment there, but that's really interesting. Um, but all of the above, storage is, as I've alluded to before, is just kind of a drop in the bucket in the overall CapEx of AI infrastructure. I'll take this chance to also say, talking about all of the above solutions for grid reliability and responding to the grid, if we think about the AI factory fully enabled outside in the yard with storage, with generation, and then moving inside to the white space where the compute is, we can actually flex the compute without pausing the workloads and maintaining the service level agreements with our partners at Benthouse and Supermicro, Emerald AI, Mercury Computing, NeuralWatt. There's many others, Pado, Soma Energy. Just had a great thought leadership piece from one of their co-founders on LinkedIn. But we're not just thinking about storage. Storage is the first line, top line, easiest thing to do. Easy, boom. It's a flexible resource right there. You could switch to storage. But we can also flex the compute, the workloads at the rack incrementally. We can shift the workloads out of that region to a less constrained region on the grid emergency days. And we can also get flexibility out of the direct liquid cooling loops, which use very little water, by the way. This is the dream infrastructure design. So it's really in all of the above. We have all of these levers now to solve this problem, and storage is really, to me, like the easiest one and necessary.
And I want to get into, I think we were seeing a few questions in the Q&A that are alluding to this, and I think it'll be interesting for folks. We started this conversation kind of looking at VPPs and energy storage as I don't want to say stopgap measure, but a sort of a way to get that lack of capacity we have in the 2030 timeframe. But as we're looking at this load increasing and we're looking at kind of a growth scenario, is there a way that VPPs, we should be thinking of them as a more sort of stable grid asset, not something that's just this sort of stopgap measure, but incorporating it more into like integrated resource plans, and how should we really be thinking about them, going into 2035, 2040, if we're also expecting this sort of continued growth curve from data center load and other loads as well.
Yeah, this is a great question. I hinted at this earlier. Look at it at the macro level. If we pair GPUs for NeoCloud, which is like it's a GPUs as a service. It's the NeoCloud tenant owner operator is providing GPUs as a service. make them smaller and pair them with storage, which solves the problem for us, right? Those 50 hours, if we can shave down those 50 hours down here, we just found 100 gigawatts, whatever the latest figure is. But smaller distributed networks of neocloud paired with storage um, is really interesting to me because that creates a virtual power plant in urban areas. So far, we've seen data centers kind of out in rural areas, um, remote areas. As we get closer to deployment of robotics, autonomous cars, autonomous flying vehicles, those are real now. You're not going to want to have those latency issues, and you'll need edge computing networks in urban areas, um, which overlay very nicely with telecom infrastructure, by the way. So small bits of neocloud compute, GPUs paired with storage. What does that do for the storage economics, for the economics of financing and purchasing the best? It completely changes the economics. And you might see 2-year ROIs where before we were really struggling to get 10 to 12-year ROIs in some regions. So if you want to talk about it like a acceleration deployment vehicle, stick a NeoCloud GPU infrastructure on your storage and have them both be optimized for grid reliability and also supporting the reliability of the NeoCloud. But one shift in sentiment that's happening coming out of Transition AI just a couple months ago in San Francisco, great conference. Um, Maybe readjusting our idea of like five nines for data center reliability. Maybe Google's comment was, let's look at 3 nines. Let's look at storage in 3 nines. Being able to geographically shift workloads again out of New York City to the Midwest ISO on the hottest day of the year. You do the computing over there. Those kinds of things are how we're going to get this. But I think pairing NeoCloud and micro data centers for AI with storage will change the economics and allow more storage projects to pencil and really pencil.
Yeah, thanks for that. And I mean, just getting back to your comment about Google, I mean, are you seeing appetite for, doing those sorts of sort of mitigation measures? Because I think part of the issue we've seen with this sort of drive to, build the biggest and best hyperscale data center is there is also a layer of competition among all these different tech companies. Are there ways to get around that? Are you seeing appetite from companies to, you know, I wouldn't say downgrade their uptime, but be more flexible in how they're going about, managing their compute load and things like that?
Yeah, well, Google is a great example. I mean, they very wisely hired Tyler Norris, famous for his Duke study, Rethinking Load Growth, a couple of years ago, which is kind of the shot heard around the world in terms of how are we gonna make all these large AI data center loads work? His argument was, if we can just find 1% flexibility, or I guess the new term to use is power optimization, is replacing flexibility, but same idea. Just 1% of flexibility in the design of an AI factory would, free up gigawatts and gigawatts of load. Google really has been a strong leader in the effort to create grid responsive um, AI infrastructure and traditional data center infrastructure. They notably recently were featured in the Wall Street Journal and other publications, kind of running down the checklist of everything we just talked about, right? Like flexing compute, thinking about storage, thinking about co-locating with large-scale generation in a direct-to-utility deal, and then also the bring your own capacity concept, procuring capacity from the local community so that they get the demand response payment benefit and kind of are flexible on behalf of the loads that the hyperscaler cannot be flexible with. So it's an all of the above approach. And I think, yeah, Google is really leading, expressing leadership there in a major way.
Great, yeah, I think they did actually. Yeah, as you were saying, I think they launched a VPP pilot, like a 100 megawatt VPP pilot a couple of weeks ago as well. So yeah, it is nice to see at least as some folks are interested in those, more innovative models. And I think we'll probably see more of that as well as, there's only so many gas turbines available. And I think as supply chains kind of get compressed, I think we are going to see folks expanding the menu of options they're looking at. So I did want to touch on just,
Oh,
oh,
can I
go
just
ahead.
follow on? And
Yeah.
we're also, I mean, we're fully working on BYOC, in alignment with our other CSPs in the space. Really just watching and pushing on regulatory environment so that we can build that out. But that's to us, that's another huge emerging tool in the toolbox to solve for this problem, the bring your own capacity problem. So we're very active in that as well. Just wanted to make that point.
Great. Yeah, good clarification. So I did want to just touch on sort of the regulatory aspect of things because we are seeing a lot of recent developments. As you kind of alluded to, FERC recently issued 6 show cause orders to the regional transmission organizations under its jurisdiction. That's requiring them to either justify or revise their existing large load tariffs to address issues for large load customers like data centers around things like co-location with existing or new generation and grid flexibility. Even with these FERC orders, there's already, PJM's already has modified their large load tariffs. A lot of states are also considering ways to incentivize bring your own power, bring your own capacity, particularly around energy affordability. So I did want to make sure we touch on how all of this sort of relates to energy affordability. I think for a lot of folks, there's, we've touched on bringing energy storage with the data center, but they're still not necessarily seeing a community benefit from that. So if you would maybe want to expand a little bit, I know you touched on this, just how data centers with energy storage can lead to community benefits, not necessarily just, the reduction in interconnection costs or something, and how that eventually leads to ratepayer benefits, but direct community benefits for the folks living around this data center.
Yeah, I'll mention a couple reasons. Having flexible load through storage to relieve pressure on the grid in the peak hours, calling it 50 hours, the 50 hottest hours of the year. That's literally how we keep the lights on in the United States. Bringing load offline is the equivalent of generating more load. So we have these emergency power plants called peaking plants or peaking generators, and they're very expensive to operate. The cost of power, if you're exposed to real-time index price, if you're exposed to real-time price like you might be in the state of Texas or some of our HPC customers are, flattening those peaks keeps the cost of real-time power down. Otherwise, if the utility or the grid operator has to start firing off peaking plants, you're looking at a very expensive kilowatt. So mechanically, the demand response function is preventing runaway energy pricing in that emergency hour or hours. So overall, that kind of is a power cost reduction when we don't have to fire off the peaking plants. Think about a peaking plant as a giant jet engine that produces electricity for X hours per year and just blasts millions of dollars, natural gas in, and then millions of dollars of cost out the other side. So, to be able to avoid firing those off is a cost saving measure. Keeping the lights on, I'd say also, if we distribute the storage into the community, so they're seeing the benefit, keeping the lights on in their house, keeping the lights on in their businesses, and selling that capacity, that capability to curtail load to the regional AI factory in the BYOC model at a pretty compelling price to make in-home or in-business energy storage affordable. The other benefit there for cost savings is peak shaving, lowering your demand charges for homes and businesses, mostly businesses, depending on where you live. So I would say those are the four or three reasons that there would be a ratepayer benefit.
Yeah, and I will also add, in terms of reducing the runtime of peakers, you're also seeing emissions benefits there because, I mean, you mentioned they're like being an extra jet engine. Some of them are literally burning jet fuel. So they are some of the, not only the most expensive, but also the dirtiest power on the grid. So, and we are unfortunately seeing them running a lot more to power grid connected data centers. And I also just in terms of, that sort of ability to have community benefit through sort of financing, the data center developer financing in-home energy storage or in-home energy efficiency upgrades. There's a great report from Rewiring America that really looks at this phenomenon. I encourage folks to find that or drop the link in the chat if I have time. Because, we do need, in terms of community benefits, I think there are more expansive ways to be thinking about this beyond just, the reduction in emissions if you're going to use energy storage versus a gas turbine, for example. But yeah, those are all great examples. And then just from a state policy perspective, I think a lot of states, there's obviously sort of what's happening at the RTO level, but in terms of states incentivizing not only energy storage adoption, but also sort of VPP growth, do you have any thoughts on sort of the near-term outlook for VPP growth, particularly among large load customers? But are there things that state policymakers should be considering to help sort of facilitate VPP adoption, again, among those large load customers? And a lot of states do have VPP programs that tend to be more targeted towards, either residential customers or sort of that smaller scale. So, yeah, I don't know if you have any thoughts on ways we can do that or. Oh, sorry, I think you're muted.
Oh, sorry, Abby. I'm going to borrow a few comments from Jigar Shah regarding the FERC statement from June 18. So he summarized it as if RTOs don't act, FERC, we will dictate the solutions. And he touched on, certainly the permitting delays, our interconnection queue is broken. There's a lot of junk interconnection requests in the queue. It's another problem. He mentioned utility incentives, maybe rewarding more capital spending over efficiency. But I think the big one is equipment cost inflation. Transformers are up, according to his figures, 89% in cost since 2019. So the infrastructure for the utility for distribution is incredibly expensive. I think, what do we want to see? We know Senate Bill 6 in ERCOT is an interesting development. Large loads over 75 megawatts must be interruptible, or those are what we call conditional megawatts. We're just seeing how that's going to affect design there. And they provisioned a fast track for interconnection, I think, is part of that bill. We're really interested in the bring your own capacity legislation or a regulatory discussion in PJM. I think that's really like becoming the near-term best lever to supercharge the build out of VPPs in these constrained areas. That's PJM, MISO, Midwest ISO, Independent System Operator. SPP is really interesting. We're seeing a lot of data center development there, possibly New England. So I think, yeah, it's all of the above, but if you come to the interconnection with a well-designed, you design the right kind of AI factory, storage, load orchestration that can adjust dynamically and breathe with the grid in real time is how we like to think of it, adjusting the workloads incrementally. You have efficiencies in your direct liquid cooling, which uses very little water, which can also shed load in unison with the workload power optimization and grid responsiveness. On top of that, these secondary or secondary markets that allow us to trade capacity at a much higher level than it is now to alleviate these constrained areas. I think that's what we're seeing, and that's what we're pushing for at a regulatory level.
Great. And with that, I do want to make sure we get to the many, many questions that we have in the Q&A box. And I think actually I have one that kind of is a good follow-on from that, which is, we've talked about all the benefits energy storage can bring, but there are also some concerns, I guess, around if you have a data center that's just charging with energy or just only employing energy storage, and that's grid connected, you're then obviously having issues where the energy storage is charging from the grid. You're still getting those spiky peaks. I wonder if you could just maybe even outline like your ideal sort of infrastructure setup for an AI factory. What are the considerations that would make them best set up to be a grid asset and not just a liability? Whether that's making sure they have co-located generation with the energy storage, keeping it to a smaller size than these sort of gigawatt scale hyperscalers, if there are ways we can mitigate the impact of those gigawatt scale hyperscalers as well, because I think those are one of the thorniest issues that grid operators are trying to figure out. And I don't know if you have a solution to that problem, but you're welcome to share it if you do.
Okay. First, I'm going to caveat this all by saying I am not a data center designer builder, not an engineer by training. I've been in the energy sector for 12 years, but I'm a bit of a generalist and a technologist. But I will relay what I've been hearing and seeing at the many conferences I've been at over the past 3 months. I think there's like 15 or 20 different conferences across different sectors. Yes, I see value in building smaller. Sub 75 megawatt size is interesting because then you might not need a capacity increase building with the capacity that's available now. I will say that our crypto mining customers, our publicly traded ones especially, are pivoting over into AI infra, which is going to take a little time to retool, but they understand energy in a very sophisticated way, and we're seeing innovation. Direct liquid cooling comes from the crypto mining sector, and that is the AI infra cooling method of choice. So we're seeing that innovation, that understanding of energy kind of help pioneer some new design ideas, but build smaller to mid-size so that you're using capacity that's already there. One, if I was developing the design from the grid in looks something like this. Storage is the outer layer for that power quality, the peak taming, either going out, hitting the grid, or the low voltage ride through issue coming in if you're in Texas or wherever, if you're in PJM. So storage on the outer layer, followed by generation. And I believe I'm borrowing this from FlexGen's presentation at Transition AI. So BESS, then generation, then you have your UPS system to further tame transient peaks, presumably in the white space. Vertiv is working on some really cool new tech, and they seem to be pretty much out front there. And then as we move inside the white space, we have load orchestration through some of those companies I talked about before, where we can really optimize the compute load and even have it respond to grid signals incrementally without impacting the SLA or the quality of service. Our partnership with Supermicro and Benthouse, the new B200s that are shipping now, are already integrated, I believe, for this kind of workload automation and grid responsive optimization in partnership with CPower, Benthouse, and Supermicro. So the load orchestration and optimization for grid reliability inside the white space, and then we get that parallel nonlinear uh, curtailment of load when we flex the workloads in the white space. The direct liquid cooling can actually do some very interesting load reduction, and we're talking about 20 millisecond response times. Imagine all of these grid responsive AI factories that can auto tune what's happening on the grid and help manage the grid and balance the grid in real time. That's when we see this design actually helping modernize the poles and wires and the kind of almost 19th century grid that we're dealing with now. The right kind of data center could act as a balancing mechanism. And actually, ERCOT is starting to classify and think about AI infrastructure, data center infrastructure, as its own utility class, as its own power platform. So we have a real opportunity here to design the right kind of AI factory.
And just a clarifying question, David, if you could define UPS and SLA for our audience.
Sure, yes. Uninterruptible power supply. So it's your short-term, if you lose power, you can still keep computing for a shorter term, and then your battery storage gives you longer term backup on top of the power quality kind of conditioning. SLA, okay, so these are some data center terms. Service level agreement, and that is the contract you sign as a data center host with your tenant to maintain uptime is probably the big one. When we say 5 nines, we're talking about, or 3 nines or 4 nines, we're talking about 99.99% uptime. We're rethinking the uptime requirement too, now that we can geographically shift loads from one ISO to another, from one region to another. And QoS is another good one, quality of service. It kind of be used loosely in conjunction with SLA.
Thank you. Yeah, I think a lot of us in the energy sector are rapidly having to become experts in those more technical AI and data center terms that we're not particularly familiar with. So thank you for that. I do love that you alluded to this sort of idea of using data centers as sort of their own utility class. A lot of the questions we've been getting in the Q&A are related to what state policymakers can be doing to sort of promote this good data center design, particularly because, a lot of this building is already happening. But, how do we, if it's going to get built, how do we make sure it's going to get built with the least amount of harm and, potentially as an asset for our grid and for our communities. I don't know if you have additional thoughts on ways that policymakers can be implementing this. I know in our work at CEG, a lot of what we're seeing is, one, implementing these sorts of measures to reduce what we're the sort of junking up the interconnection queue. So submitting supplemental interconnection requests through things like requiring either like exit fees or any other sort of monetary commitment for developers, so that if they do submit an interconnection request and then they pull out of the project, there is a fee associated with that to just reduce that sort of, jumping around to various locations and shopping around. There's things like minimum demand charges as well. So if the data center is paying for, say they're going to have X amount of demand, having to pay for a minimum of that, even if their energy usage is actually less than what they thought it was going to be. Supporting things like co-location and pairing with zero emission sources of backup generation. So using things like battery storage as opposed to a gas generator or something like that. Those are some of the things we're seeing already in a lot of states. But there's it's a bit of a frontier here, so we're all kind of adapting things as they come up. But yeah, I don't know, Dave, if you had any other thoughts to add.
The interconnection queue, like the junk requests in there are a huge problem. Um, Anything we can do to, yeah, figure, applying to multiple locations. We need to free up the interconnection queue. But I think, if we have, I think building a fast track, which is kind of where we're moving towards. Again, if you show up with the right kind of data center, and the utility can say, okay, you're asking me for, let's call it, let's make it like a good size, like 50 to 75 megawatts. That's now considered like kind of a mid size. It used to be 10 megawatts, but still very large load, but it's under that 75. Okay, I'm asking for 75 megawatts in PJM. And the utility may say, okay, I have 20 for you in this exact location where you are due to transmission constraints. Uh, but the balance of that will have to be those are I'm going to give you 20 firm, let's keep it math easy, 25 firm megawatts, and then the other 50 are going to be conditional or flexible that we can pull back anytime we need them when we get into trouble on the hottest days of the year. If you show up enabled to do that, so that you can go offline for, again, this is just I'm just using a number, an easy number, 50 hours a year, depends by region. Um, there should be a fast lane for you to move through in a year or less versus 3 to 5 years, because you're actually solving a problem. And, we're already, our customers come to the table fully enabled and ready to enroll in, all of the above utility and ISO level grid reliability programs, from fast acting generation VPP type programs to the, simple capacity. So showing up with all of the design and the intent, there should be a fast lane for you to participate in the DR markets that already exist. And they're more of them. They're more focused on the ISO level, but there are plenty of utility level programs too. And then there's the BYOC structure that's emerging, which is very interesting.
Yeah. I did also just want to touch on another question we had, which is, just looking at the accuracy of all these sort of load projections. Yeah, as I mentioned, the sort of upgrade to the LBNL estimates from even just from 2024 to 2026. And I will say that is something that is a challenge, is estimating data center demand, both because this growth is exponential and we just don't have a ton of data on data center operations. And as things evolve and things get more efficient, I mean, David, you mentioned the innovations in the cryptocurrency sector around cooling. It is a challenging load to predict. I don't know if you have any thoughts on sort of how we can, how accurate any of these projections are, or how we should be thinking about those projections, if they're more like guidelines, or if, we should be taking them with a grain of salt, or if they could be even just underestimating load.
Boy, yeah, it's really hard. It's really hard to model this. I will say, like, I'm in the room having conversations with our technology partners who are really bringing like breathtaking innovation to solve this problem, like across the spectrum of providers. And um, were some of those load growth numbers were basing on just running everything flat out, right? Which is what we've been doing for traditional data centers. They just run flat baseline. Everything's at maximum, computing speed, power, efficiency, optimize everything. The dynamic nature of what we're talking about for um, like the right kind of AI infrastructure that we need now to make this all work in America and keep the AI innovation here at home, um, and win this technology race to the moon, is workload orchestration. It's workload infrastration, orchestration. It's applying the right kind of purpose-built storage to the infrastructure. And yes, we're seeing all kinds of efficiencies emerging. Partners that are modeling every electron flowing. Vertigris is an interesting company. They can model every electron over every bus bar and say, oh, okay, data center, you think you need 100 megawatts, but some of your, bus bar ratings are, overrated. You can actually get away with 75 megawatts. So with AI, in the mix now, and the kind of modeling we can do, digital twin modeling and orchestration of workloads, storage, new types of generation, geothermal is really interesting to look at again in terms of getting rid of waste heat and then also cooling with deep well geothermal. So I think, yes, at the same time, we'll see a reduction of actual load needed for the amount of compute that we're aiming at. But what is the economic term? Jevons paradox. With more with more with increasing efficiency, you'll see more use as costs come down. So I don't know. I don't know. That's a $1 million question, but I am hopeful about all of these advances that we're seeing of optimization and efficiency.
All right. Well, I think, do you have a hard stop at 3, or do you have time for one more question?
No, I can keep going.
Great. Yeah, well, for folks that we don't get to your questions, we will, be following up with you via email. So, apologies if you didn't get to your question, but we will follow up. Do you have any thoughts on sort of the relationship between large load and storage, as storage is expected to have decreasing ELCC or effective load carrying capacity values in the future as penetration of storage increases on the grid, especially in PJM, for example? Is there any worry that these large load customers are going to be getting less value for their storage and need to procure any additional capacity from other sources because of that?
Great question. Boy, that's a timely one too. We are seeing erosion of DR capacity in ERCOT due to more storage coming online and some other generation types. But yeah, that's a very real very real risk. Uh, Unclear. I'm unclear on what the guidance would be there. We're monitoring that. I think that's a very real concern. If we look at the rising value of capacity, though, and we start having new markets, to quote Jiggershaw again, the value of a kilowatt or a megawatt to a GPU right now will never be higher than it is between now and 2030 or 2031. If you have power, it's almost like name your price to a GPU. So we expect the next 3 or 4 years. We don't know. I mean, who knows what's going to happen in 2030 and beyond. But to us, demand response is the way to get to 2030. It's a no-cost option. It's something we can deploy right now. And I think storage will continue to be incredibly valuable as it moves through its life cycle, because we expect the value of capacity to rise at a pretty dramatic rate over the next 3 years, let's call it, and near term, especially the next 12 months.
Yeah, definitely. All right. Well, with that, thank you so much, David, for even staying over time to get to some of these questions. It's been a great conversation, and I thank all of you in the audience for sticking with us. And this is definitely a topic we're going to keep covering at CEG and CISA, so I'm sure we'll have additional webinars around this topic. But yeah, I want to thank you all again for joining us, and thank you again, David, for joining us as well.
Thanks, Abby. Thank you all.